a recap on the strategy for defining function templates. You want to write a regular, in other words a non-template function first, then you want to debug, or in other words test the function, and then you'll go and convert the function to a function template. It's a good idea to not separate out the declaration and definitions of your function templates. And if you don't separate out the declarations and the definitions, then you want to ensure that the definitions of your function templates are defined before the function templates are invoked. Of course, you can also define your function templates in header files and then include it where it's needed. As I mentioned in a previous video, you can separate out your function template declarations and your definitions in this way. I just have the print example again, so we do cout formal p, so we print out what we pass in. So in main, I call the print function and I specify this explicitly to be int, so the type argument will be int. If I build and run this, we'll get 55 printed out. Now with function templates, it's actually best to avoid separating them out in this way. I'll cut that out and I'll paste it up here to make sure that we have the definition. So instead of separating out the declaration and the definition, I just have the definition up here. With modern compilers, you should not have any issues separating out your function template declarations and definitions, but still I'd recommend when it comes to your function templates to stick with just having a definition and not separating things out. Instead, what you can do is you can define the function templates that you need in a header file. Maybe you have a bunch of helper functions, then put those in a header file, and then you can simply include that header file where you need it. And in that way you can sort of clean up your source file a bit, and you can also use those helper functions then in multiple source files, even across multiple projects. Because it's just a file, so you can copy the file over and then include it in your source file where you want to use it. A summary on template instantiation. Template instantiation is the process in which the compiler generates a function, class, or a struct definition from a template. And basically what happens during the process of generating a function, class, or struct definition from a template is that the compiler replaces every instance of a type parameter, the placeholder types, with the type argument or arguments that are specified by the programmer or that are deduced by the compiler in the case of a function template. As I mentioned, templates are instantiated only once. Subsequent function invocations or struct or class instantiations with matching type arguments will use the already generated definition. As I mentioned in the lecture on class or struct templates, you want to define your class or struct templates in header files. And in this section I'm going to explain in a bit more detail why that is, and some of the problems that you can run into. Templates are instantiated at compile time, and to instantiate a template class or a struct, the compiler must have access to the member function definitions. Now source, or in other words .cpp files, also referred to as translation units, they don't know about each other, so one source file will not know about another source file at compile time. That is resolved at link time. At compile time, the compiler will know about the files that we #include because #include is a preprocessor directive. So what it boils down to is separating class or struct templates into .h header and .cpp source files, as we are familiar with non-template class or structs, while separating them in that way can lead to errors. If a class or struct template definition is in one file, typically in a header file, right, but its member function definitions are in another file that is not included in the source file that is being compiled, then the compiler cannot see the member function definitions and generate code for them. The compiler will allocate memory for object data and build calls to the member functions, but it's not going to find the member functions. It's going to assume that the member functions are being built or has been built in another source file. And so since the member functions may be defined in another source file, we don't get a compiler error, because the linker will typically make the connection at link time. And when the linker does not find the code generated for the member functions, then we'll get a link error. And to avoid these complications, your class or struct templates are typically defined entirely in your .h header files. I'll show you a few examples next in Visual Studio. For this demonstration, I'll use this entity class that we used in a previous example in this lesson. It is a template class, and we have a constructor and a setter and a getter for the member, which is of type T, which is that type parameter. And I've separated out the declarations and the definitions, so here we have the definitions. And then in main, all I do is entity, so I instantiate entity1, I specify int as a type argument, and I pass in 55 for the constructor, and then I do console output entity1.getMember, and if I build and run that, we get 55 printed out. Now what happens if I take all of this stuff here, and maybe I want to separate things out, so we have a header for our class definition, and maybe a separate source file for the definitions of the member functions. So let's go and create. a header file, add a new item. Once more, this is just a generic entity class for demonstration purposes, so I'll call it entity.h, and I'll add that. I'll select all of this and cut that out. Paste the entity class template definition within the entity.h file, along with the definitions. We have the definitions down here. Then I'll go back to main.cpp. And when we include that header, we do pound include entity.h. The red squigglies go away. If I build and run, this will work fine now. But let's say in this entity.h, let's say we want these member function definitions to be in a separate source file. I'll go and right click on the project, add new item. We want a .cpp file. Call that entity.cpp and I'll add that. Go and cut those definitions out. In entity.cpp, I'll paste those in. Now, of course, it doesn't know what this entity is, so we pound include entity.h and those squigglies go away. We may expect this program to run and to work fine now. This is how we typically would go about doing it. With non-template structs or classes, this is typically how we would do it. You have the class or struct definition, basically that interface you have in the header file, and then your implementation of the member functions will go in a separate source file. So we would expect this to work. But if I try and build and run this, Control F5, we will actually get linker errors. LNK, that's a linker error, unresolved external symbol. This again is because templates are instantiated at compile time, meaning the compiler is going to generate an actual definition from that template based on the type arguments. But we talked about what template instantiation means in previous videos. Compiling happens before linking. Now because we include this entity.h header file into the main.cpp file, remember this is a preprocessor directive. So main.cpp will know about the stuff that is in here, in the entity.h file, at compile time. But the main.cpp file will not know about the entity.cpp file contents at compile time. That is something that happens or is resolved at link time. And so that is why we get linker errors. Because let's just go back to entity.h here. At compile time, the compiler is going to try and instantiate this template class, but it's not going to have all of the information that it needs to instantiate this template. Because again, this is done at compile time, and those definitions are in a separate file now. It is in the entity.cpp file. We do not include the entity.cpp file in entity.h. One solution to this problem is we can go back to main.cpp and we can include the entity.h file, and then we can include the entity.cpp file. And that way at compile time, the compiler is going to have all of the information that it needs to instantiate the entity class template and build around this. And you can see that works fine. If you think about it for a second, we don't actually have to do this entity.h, this line right here. So I can comment that out and I can build a run. And that works fine. It prints out 55. And the reason is if we go over to the entity.cpp file, we include the entity.h file right here. So that is already included in the entity.cpp file. So in other words, all of the content in entity.h, this entity class template, that content is going to be included up here at the top of the entity.cpp file. And then in main.cpp, we include entity.cpp. So at compile time, the compiler will have access to the definitions of those member functions, and it needs to have access to those member functions at compile time to instantiate the template. Now, as I mentioned in previous lectures, we don't want to do this. We don't want to include .cpp files. It's a well-known convention in C++ that your header files are your interface files, and your source, or in other words your .cpp files, are your implementation files. So it's not common to include .cpp files, even though you can. Because of these types of complications, it's best to define your class or struct templates entirely in your header files. If this was a non-template class, so if entity.h, this class, if this was a non-template class, just a regular class or a struct, then the compiler won't have to generate a definition. It's going to exist already. I'll actually uncomment that and I'll remove this line right here. This is what we'll typically do with non-template classes. We'll include the header file for the class of the struct where we need it. And what does that do? It's only going to copy and paste the content that is in that header file. Now once again, notice that the definitions of the member functions are not in this file. It is in a separate source file. Basically, the link between the class or struct definition in the header file and its member function definitions in some other source file are linked together at link time, which follows compile time. Now, as I mentioned, template instantiation happens at compile time, and that again is why we get those types of errors and these types of complications. As I mentioned, we don't want to include source files or .cpp files, we only want to include our header files. Now there is one more way that we can separate our template classes or structs into header and .cpp source files, and that is if we use explicit instantiation. So in this next section I'm going to introduce the difference between the inclusion model and the explicit instantiation model. Starting off with the inclusion model, this is the model that we are familiar with already. The member function definitions are included in the .h header file along with the class or struct template definition. So in other words, you don't separate things out between a header file and a source file. This method provides access to the complete template definition so the compiler can instantiate the template for any type arguments provided. Now those member function definitions will be included in every file that uses the class or struct template, because they'll be including the class or struct template definition along with the member function definitions, and not just the class or struct template definition as you would typically do it. Now because of that, the compilation times can increase when the project and or the included files are large, but still this is the recommended model unless compilation times are a concern. Next we have the explicit instantiation model, and in this model we will have explicit template instantiations for specific members or types. Code is once again separated into .h and .cpp source files, and the template is explicitly instantiated in the .cpp file, typically at the end of the source file following the member function definitions. We have an example for the syntax of an explicit template instantiation. You use the template keyword followed by the name of the struct or class template. In this example, entity followed by the explicitly specified type arguments between angle brackets. Now the explicit template instantiation is going to generate object code that the compiler will see and use to compile the object that we create of the same template type. With this method we get faster compilation times, but the type usage is limited to those that are instantiated ahead of time. For example, if we do explicit instantiation of an entity with a type argument of int, then we can only create objects of that type in our code, such as in our main.cpp file for example. Let's look at a quick example in Visual Studio. In the main.cpp file, all I include is the entity.h header file. As I mentioned, we do not want to include source files. Then in the header file, I have the definition of the entity class template, and I'm going to include the header file in the entity.cpp file, and then we have the definitions for the member functions right here. Then I want to do an explicit instantiation. This is very simple. All I use is the template keyword. I do entity, and then I provide a type argument, int between angle brackets. Back in the main.cpp file, I create an object entity1, which is of type entity. Now entity is a template. We pass an int here for the type argument, and then I do entity1.getMember. Let's build and run and see what happens. This builds and runs fine, so we get 55 printed out. And notice again with this, we only have to include the header file. But the problem is the compiler is only going to know of this right here, this explicit instantiation. So we can only create objects of this type. And with that type argument, if we change this here to a float, something like that, now we won't get any red squigglies, but if I try and build a run, Ctrl F5 to build a run, we'll get that link error again, to unresolved externals. So we can do another explicit template instantiation. In this case I pass in float for the type argument, and then this here should work, because we can now construct objects of this type. Build a run, and that'll work fine. But again, if I change this here to a double and I build a run, once more we'll get those unresolved external errors, and we'll have to go back and create even more explicit instantiations. So for every other object that you create with a different type argument, you'll have to create an explicit instantiation. So that is why it is recommended that instead of doing this, you simply, I'll just cut that out and remove that line as well. Go back to the entity.h header, and I'll make sure that the definition of the class, the entity class template, and all of its member functions, its member function definitions are all in the same file, in the same header file, entity.h, and I include that in the main. And now even though I have a double, I can build a run, and that'll work fine. I can even do a char and pass in h for the parameter, and build a run, and that'll print out h. And I don't have to provide an explicit template instantiation each time. Just put everything in your header file, whether the member functions are defined within the body of the class, or whether the declarations and definitions are separated out. And in this way you avoid those complications, and especially for small classes like this one, I prefer to do the member function definitions within the body of the class. And in that case you have to do less typing, you don't have to repeat this template stuff.